Okay, hi everyone. Welcome to lecture 17. Last time we saw how to construct linear size IOPs for the NP-complete language rank 1 constraint systems. It's a restriction of quadratic equations. For the record, you can do the same for quadratic equations. We just didn't see that. It requires one new idea, but the point is that we were able to show how to achieve linear proof size, but there was one component missing. Throughout, we made extensive use of encodings using the Reed-Solomon code, univariate extensions, and we kind of built everything, but for the fact that we needed a tester that with a small, we'll see today, logarithmic number of queries in the degree is able to ensure that some written function is close to the Reed-Solomon code. Okay, so that's the goal for today. So we'll be studying proximity testing to Reed-Solomon code. As a reminder, this is the code. Just some features to remember from last time. We have decoupled the domain from the field. So it used to be that whenever we have studied linear and low degree extensions with multiple variables, the domain was always field to the number of variables, okay? Whereas now the domain is explicitly some subset L of the field. You will see later today why we want that. We'll have a recursive procedure that kind of reduces the domain, and we can't sort of reduce the field, okay? And sort of the set of valid encodings that we used last time was we have some given degree, right? And we want all functions, we consider valid sort of encodings to be all functions such that when you interpolate them, you get a specific degree, right? Of course, this makes sense only when the degree is, is non-trivial only when the degree is like less than the size of L, or at least less than 1 minus the size of L, right? Because every function by interpolation has degree at most size of L minus 1, okay? But the regime in which we're using this is when d over the size of L is like, some small constant. So think of d as being like 100th of the size of L, okay? And so that means that, not all functions of this form are in the set, only some. That's what we want to test, whether the function that is given to us as part of a PCP is, or an IOP, is close to this set. So completeness means that, if the function really is in the set, the test should accept with probability 1. Soundness means that if the function is delta far, okay, then the test should accept with at most some error that, of course, will depend on the distance. And you should think about it that the kind of functions we're looking for is that if we are delta far, where delta is like some sort of small enough constant, say a 10th or 100th, okay, then we're accepting with some probability it is bounded away from the 1. So at most, I don't know, 3/4 or at most 9/10 or something like that, okay? This is the regime in which we have been using low degree tests throughout this entire class, including in the analysis of the IOP from last time. We have also come across specifically this code. We didn't call it as such, but we did talk about univariate low degree testing. That was a warm-up to multivariate low degree testing, if you remember. And we have already seen that we do have a very nice test that uses d plus 1 fixed queries and a d plus second random query that achieves a pretty good soundness error that basically soundness error goes down linearly with the distance. So the bigger and bigger distance, the soundness error goes closer and closer to 0. That's like kind of very nice behavior. And the way it worked is you interpolate the answers to the fixed d plus 1 queries that gives you an alleged sort of candidate polynomial, and you check consistency of that polynomial at some other random location. We also saw that d plus 2 queries are necessary to achieve any non-trivial soundness error because any answers to any d plus 1 queries, doesn't matter how they're like located, are consistent with some code word in this set, okay? So, and this is fine, when the degree is much smaller in the domain, but in our case, the degree is going to be linear, the size of the domain is going to be also linear, so this just not going to work, all right? So we're going to need the query complexity to be much less than D. So what do? Well, these limitations are really just about proximity tests, where there is just a test and the code word, okay? And the test is all alone trying to do its testing task. But we'll do something else today, which is we're gonna ask the prover's help, which lead to, you know, what are usually called proximity proofs, okay? So you're doing a proximity task, but somebody's sending you some additional information that helps you do the proximity task, you know, this way, okay? So the goal for today is we're going to construct a proximity proof for the Reed-Solomon code. Are there any questions about the slide? I'm going to say proximity proof more precisely in the next slide, but as far as the material in this slide, are there any questions? This will be the third proximity, I guess, object we'll see in this class. We've seen linearity testing, we've seen multivariate low-degree testing. This is going to be proximity proofs for univariate low-degree functions. Okay? All right, I don't see any questions, so let's proceed. So we want proximity proofs. Okay, so let's try to say it a little bit more precisely, you know, what is the object we're looking for. We're going to say that a pair of interactive algorithms, P and V, is a so-called IOP of proximity, shorthand IOPP, for this set, okay, if two conditions hold. Completeness means that if the function that is given really is in the set of low-degree code words, then the honest prescribed prover is able to make the verifier accept with probability 1, and the verifier has oracle access to the function being tested, obviously, right? But it may receive other oracles as part of this interaction, okay? Soundness means that if f is delta var, then regardless of what the prover does, the verifier interacting with the malicious prover and having oracle access to the function, it will accept with at most probability there is some error that depends on the distance, okay? This is entirely analogous to the normal proximity testing, except that we have the new actor, the prover, okay? And so kind of pictorially, an IOPP looks like this, right? So this is the fixed object that we're talking about. It's explicit, right? It's right here, right? It's right here. So it's not something the prover decides. This is like fixed in advance, okay? And then the prover gets to send me, you know, whatever he wants as part of the interaction to help me out with these conditions, okay? So somehow there is this kind of oracle input to the protocol rather than a normal input to the protocol. Now there are some parts of the input that are still given normally, right? I mean, the verifier knows F, right? It knows L, it knows D, right? So it knows what code we're talking about. So these you can think about that there is explicit input to the verifier. And you know, the efficiency measures for discussing these objects are the same as the ones we've been discussing with IOPs, except that now the query complexity will additionally charge, you know, will additionally count queries to the sort of original object as well. Okay, so the total query complexity needs to be small across all oracles. Otherwise, you can sort of cheat, right? For instance, if you could just send me the polynomial here, and I could do an identity test between the polynomial and this one, right? So I really need to charge you for the queries across all oracles, all right? And now for today, we're gonna restrict our attention to smooth domains. Okay, if you remember from last time, there was a theorem that we wrote down and I said we're gonna only be thinking about fields that are smooth, okay? So we're gonna focus on domains L that are cyclic groups, okay? Whose order is a power of 2, okay? So what does it mean? It means that, you know, you look at F, it's a field, you look at F star is the multiplicative group associated to the field. That one has various subgroups, and I'm saying that what we want is subgroups that are sort of power of 2 that is like large enough, okay? Why? Because the theorem is going to be about that. For every F and for every smooth domain and for every degree that is that makes sense, we're going to construct an IOPP that has logarithmic round complexity, linear proof size, which means that in addition to this object, which is kind of not part of the protocol, we're going to send an amount of information as oracles that is proportional to the original object. Okay, so it's a linear amount of information. This is in the linear proof regime, which is our goal from last time. In fact, the prover itself we didn't run in linear time, so it's very nice. The query complexity is going to be logarithmic, so will actually be the running time. And the soundness error, I mean, this is a bit of an annoying expression, but the point is that the expression is kind of qualitatively behaves like the basic test that asks d+1 queries or d+2 queries, roughly 1 minus delta. It's not exactly like that, but it qualitatively behaves like that. Okay, we'll see a more precise expression later. The protocol behind this theorem has a name. It's called FRI, stands for Fast Reed-Solomon IOPP. Okay, so at various points I will be referring to the FRI protocol. Okay, so now you see here there is a question that is a smooth domain just one whose size is a power of 2? It's not just as a power of 2, it also has to be a group. Okay, so I can, if a field is large enough, I can always take a subset that is a power of 2, but that's not what I'm saying. I'm saying is that the domain is generated by a single, so first and foremost, every multiplicative subgroup in a field is cyclic, okay? And I want the domain to be a group, okay? And if you want something concrete in mind to think about, you can take, for example, canonical example would be you take a prime field, Fp, so P is a prime. Fp star has size P minus 1, okay? Why? You throw out 0, right? And so you're left with all the non-zero sort of integers modulo P. And what you're going to want is you're going to want 2 to the k to divide P minus 1, okay? Because if 2 to the k divides P minus 1, then we know there's going to be a subgroup of size 2 to the k. Now, what is 2 to the k? Well, 2 to the k is going to be the size of L. So if we want, for example, to work with degrees d equals 100, and we want like a blow-up factor from d to L to be, say, 10, that means we need L to be like 1,000. So for example, you would want 2 to the k to be 1024, right? That would be a power of 2. Okay? Hopefully that answers the question. Now, these type of theorems one can prove for more general domains. They don't necessarily have to be exactly a power of 2. You can have like a power of just a bunch of small primes. Or you can consider additive subgroups, which means basically vector spaces, okay? Essentially, it's like pretty much anything that is like reasonably FFT friendly. I'll come back to that in a moment. It is a very nice question to try to prove something like this for every domain or indeed every field. And my personal opinion is that one can prove it, just probably requires some work. I even have maybe some idea where to push in a direction if you're interested to think about it. So this IOPP for sort of the Reed-Solomon code is not just a component of the protocol we saw last time, but it is really important in practice. This is something that is, probably running as we speak somewhere, sort of in Ethereum. So it's a very practical algorithm, protocol. But not just that, there is a very nice sort of interplay, not just of sort of practical considerations, but of like deep mathematical questions, and somehow studying sort of algorithms like the ones that underlie this theorem, or sort of understanding what are the limits of those techniques, sort of raises a variety of sort of elegant and sometimes hard questions in coding theory. We'll see maybe more of that next time once we analyze it. Today we're primarily going to describe it. So the goal for today is kind of describe the algorithm under this one and to gain some intuition for it. Are there any questions for this slide? Okay, I don't see questions, so let's continue. So the algorithm, the protocol, the FRI protocol, is inspired from the fast Fourier transform. And specifically, the canonical fast Fourier transform, the one that probably you've studied in undergraduate algorithms. And I'm gonna half of the slide will be just reminding you what is the fast Fourier transform and how it looks, because we're going to be sort of using it to design the proximity proof. So if you remember, kind of the premise of the fast Fourier transform, the canonical one, the radix 2 one, is that we can take any polynomial and kind of split it in even and odd coefficients, right? And then you sort of use this divide and conquer approach that says, look, if you want to evaluate a polynomial on a smooth domain, right, which is a subgroup whose size is a power of 2, then what you should do is you should first evaluate the even coefficients on all the squares, evaluate the odd coefficients also on all the squares. This is kind of a subroutine call, right, the recursive call. And then, so this is the divide part, and then the conquer part is you combine them in linear time. So you kind of do a one pass and you kind of assemble one half of f and the other half of f, right? For the sort of the even powers and the odd, for the positive powers and the negative powers. You know, what's that -1 there? It's just, you know, you can think of you can either count -1/2 to 1/2 or like 0 to 1, right? So this is the fast Fourier transform, the nested structure that as you square the domain, it's contained in itself, enables the recursion. And each of the two subproblems have half the size, and recursion depth is logarithmic. Okay, and then this gives you this sort of very familiar recursion that the number of operations to solve a problem of size L is 2 times L over 2 plus linear work for combining, and this works out to be the n log n that makes the FFT sort of powerful compared to the quadratic algorithm that naively for evaluating the polynomial on the domain. All right, what's this got to do with low degree testing? Well, the point is that if you have some function f defined over the smooth domain L that has degree strictly less than d, notice that I'm starting to use strictly less than, okay? Then it is the same as if you are looking at the odd and even coefficients defined over the square of the domain, and they have strictly less than half the degree. Okay? So we have this one problem of size d is equivalent to 2 problems of size half of d. Okay? And again, I stress from now on, just for notation convenience, because we're working with powers of 2 and counting from 0 to like power of 2 minus 1, it will be easiest to think of strictly less than. So from now on, everything I write with d is like strictly less than, okay? And you know, sort of this basic kind of observation suggests, okay, could we maybe devise a divide and conquer approach to low degree testing as well? Okay? So that is kind of the starting point, okay? Any questions about this? I mean, eventually we'll do something that is not the fast Fourier transform, obviously we're solving different problems, but the underlying structure that enables one is precisely what will enable the other. And that's not just true over this domain, but pretty much over any domain on which you give me like a nice fast Fourier transform, one should be able to write basically a nice proximity proof. No questions? Okay, so all right, so we have the FFT. So let's go and try to devise some divide and conquer approach. So let's try something pretty basic, just recurse on each subproblem. So here is the function that we want to test. Here is the sort of prover and verifier. Notice that the prover receives the function f explicitly. The verifier can query, has query access to f. One idea would be to say, okay, the prover could just look at the polynomial that is supposed to be represented by f, right? Kind of take out the even and odd coefficients of that polynomial, evaluate them over the square, the domain, like over all the squares, and just provide them to the verifier. You know, at this point, the verifier, what could it do? It could just say, okay, well, you know, are they really the correct ones? It could just check this relation at a random point, right? this is supposed to be a polynomial identity, so why not check it at one random point or more random points? And then you could just say, look, recurse, okay? Like we are left to check that G and H defined over L squared have degree D over 2. Let's just kind of push it down, okay? So this approach is a reasonable start, but it has some issues. One is fairly obvious, another one is maybe a little bit more subtle. And what do you have any sort of opinions about this first attempt? So let me ask specifically, how many queries do you think the verifier will ask in the end once you unroll the recursion? Come on, let's have some interaction. Don't you have any guess?
It seems that we are doing one for each node in the tree, in the recursion tree.
Yeah, therefore?
Well, so if we say if we define the recursion depth to be, well, I guess it's,
so there's a suggestion by Ryan to be d log d. That is overcounting. It's a little bit less than that.
Then is it just d?
Yeah, d, right? So because we're doing a constant number. I mean, we're doing basically 3 queries, or let's say order 1 queries per node, and there is like d nodes, right? So there's a linear number of queries. This is the recursion. You know, I mean, it's a bit of a silly thing. Q of d is 3 plus 2 times q times d over 2, right? That's order of d queries. Okay, so that's like definitely not within the ballpark where we want it to be. So, you know, whatever this protocol is doing, it's not doing a small number of queries. But let me highlight another more subtle issue, which is that this is actually not even a test, okay? It exhibits something that we're going to have to explicitly deal with, which is distance decay. I want to explain that, okay? Because you could say, well, maybe it's just like an alternative way of doing like a linear query test, like the basic one. So maybe that's not so bad. We can try to improve it somehow. But I want to claim that this is not even a test, okay? And here is kind of the picture you should have in mind. Suppose that we start with a function f that has, let's say, distance 40%. So, you know, there's like, I think there should be 10 squares here. You know, 4 of these squares are kind of color black, meaning that those are errors. So you can think about f is mostly 0, except that, you know, it is, I don't know, 1 at 40% locations, okay? And I want to claim, and I'll give an example in a moment, that you can derive G and H correctly, okay, for the underlying polynomial. And yet, G and H are going to be actually closer to low degree. Okay, they're each going to have 10 errors out of 50. Okay, so of course they're defined over like half the domain, so they have like maybe 50 locations. Okay, and this is something that should worry us, because if we start with something far, and each recursion it's possible to get closer and closer, we'll end up at the end of recursion with something that is low degree, and then the verifier will say, yeah, I accept, right? You know, so it's important to, through the recursion, to have a distance preservation. Now here's kind of the example. It's a bit hard to kind of see, but basically, even if for every mu you always have this relation, you can set things up so that some things cancel out when you do this kind of sort of a combination to obtain the odd and even. Roughly speaking, I could set these blocks to be all ones, all ones, all ones, and all minus ones, okay? And intuitively, the even coefficients are obtained by basically summing a f on the first half plus the second half divided by 2, okay? Because the even coefficients is when you kind of combine sort of like every point here corresponds to a point here and its minus point here because they both square to the same element, okay? So you have a contribution from here and from here. And for the even coefficients, you add the contributions and divide by 2, okay? So here you're gonna get something that is non-zero, but here you're gonna get something that is 0, okay? And for the odd coefficients, what happens is that you take, I will kind of, we'll have this expressions very explicitly in the next few slides, but for now, just intuitively, for the odd coefficients, the way that the contributions happen here, even in the honest case, is that you subtract contributions from the first half, or rather, you subtract contributions from the second half to the first half, okay? So over here, you're gonna get this one minus that one, which is 0. And here you're gonna get this one minus that one, which is something non-zero. So basically, the punchline is that the adversary could set up the errors so that when you have this deriving the odd and even, the evaluations of the odd and even functions, half the errors disappear because they were kind of set up to kind of cancel each other out. And this is worrisome. Like we are getting, if the distance drops by half each time, and you know the number of recursions is super constant, now pretty soon we're going to be too close to detect it with, say, with a constant number of queries, okay? So that's like problematic, okay? So we'll see, now maybe let me just maybe write down the expression that we'll see very soon. G at some location, I don't know, omega squared equals f of omega plus f of minus omega divided by 2, and h of omega squared is f of omega minus f of minus omega divided by 2 omega, okay? So this is kind of local maps that let you derive g and h from f, and you know, we'll prove that this is the case even in the honest case. But the point is that, you know, even if the adversary really makes you accept always with its consistency checks, it can just basically inch its way, not even inch its way, jump its way from far to low degree to close to low degree. And in the meantime, you don't notice no problems, and at the end, you're gonna check that the base case is in low degree, or it's like, yeah, it is, because you got there in the meantime, okay? So there's something very subtle that is happening. It's not just a number of queries, but somehow even the very idea of halving the domain, currently it is failing, okay? So we're gonna have to do something about it. Is this clear? Okay. Okay, what do we do? So the idea is that instead of kind of recursing each subproblem, we're gonna so-called first fold. Okay, let me explain what that means. So the idea is to start the same way. The prover still sends me the valuations of the odd and even coefficients on the squares. But then the verifier is going to sample some random field element, send it to the prover, and the prover is going to send back a folding, right? It's going to do a random linear combination of G and H, okay? The prover will sort of send it back, right? It's still defined over L squared, right? Because it is just a linear combination of G and H. You know, I can check that it is related indeed to G and H, okay? And then we can recurse just on F sub alpha, okay? All right, let's try to understand the intuition behind this protocol. First and foremost, at least query-wise, we are in the right ballpark. We're making, you know, some constant number of queries per recursion, but now we have only one recursion, so we're down to logarithmic. That's good. And does folding make sense? Does it sort of behave correctly with respect to degree? Let's first build some intuition, the noise-free case, okay? So suppose for a moment that the adversary is only trying to cheat by sending functions that are actually, that sort of have no noise, okay? So one way you can think about it is to say, okay, well, first, let's say in completeness if it works. If degree of f hat is less than d, then we already discussed that the degree of h hat and g hat are strictly less than d over 2. The fact that I take a linear combination shouldn't change the degree. It doesn't, right? So that's fine, right? For soundness, let's suppose that we started out with a function whose degree was at least d. Then we know that either the, why did h come first? I don't know. But either the odd coefficients or the even coefficients have degree at least d over 2 as functions. In which case, I argue that the linear combination will have degree at least d over 2 with extremely high probability, at least 1 minus 1 over f. Why is that? Well, in general, if you have just two polynomials and you take a linear combination, there's only one choice of alpha for which it's going to kill the largest monomial, right? So either they both have the same degree, okay? They may even have the same monomial, but the alpha here is gonna like kind of randomize the largest monomial in the two of them, right? And you're gonna get a sum that only for one value alpha it's gonna disappear. Otherwise, you're just gonna get the same degree, okay? Most of the time, for almost all alphas, the degree of the linear combination is the same as the largest of the two degrees, okay? So I'm not discussing a noisy case. This is just talking about actual polynomials. But this is telling us that random linear combinations preserve degreeiness in the soundness case almost always. Okay? So this is to say that there is at least some reason to, there is a role for this alpha to play, right? There's some randomness that we rely on, right? It's important, right? Of course, without the alpha, I can't just add them up. I can't just do g plus h. Maybe it just happens that, I don't know, they cancel each other out, and from something that was high degree, now the sum is like 0, okay? So the alpha is very important, and it's coming up here, okay? Now this doesn't tell us anything about testing. It's just making sure that we have some sanity checks and some basic intuition about the folding. All right? Are we fine with this slide? Okay. Now, but really what happens in a noisy case, right? So let's consider a noisy case. Suppose f is delta var. Okay, and so we have again this picture from before that will continue to happen. I mean, g and h can have this noise. I mean, we just said earlier that you can set up the noise on f so that g and h, even in the honest case, or honest, I mean, you derive g and h in a way that passes the consistency test, right? So that, this one passes, but yet somehow the noise goes away. But look, if we take a random linear combination, intuitively you would expect this kind of mismatches to kind of both show up, okay, intuitively. With high probability, like if you have this type of behavior, they should both count, okay? Now, this is just intuitively. We'll actually not prove anything like that in this lecture. We'll just take it as a intuitive statement. We'll prove it in the next lecture, and sort of the fact that something like this really does happen is some fundamental facts about how linear codes and subspaces behave. Okay, it's rather non-trivial. But intuitively, the folding seems to address the private problem of preserving distance. We started with 20%. Maybe you can set up things to cancel each other out, but the canceling, will at best kind of do this type of this is kind of the worst case scenario, and then you can recover it back. Okay. So that's fine. So to a high level, we have folding has eliminated this problem of decaying distance. Yet, the prover could still try to decrease distance by sending functions that are inconsistent with one another, right? It could just try to send g and h that slowly kind of moves away from f closer to low degree by violating some of these, right? And then maybe it sends f sub alpha that slowly moves away from this random linear combination, which is kind of what this is, and tries to move closer to low degree, right? So that over recursions we get closer and closer to low degree. Okay? these are some sort of inconsistency attacks, okay? Well, I mean, we have these consistency checks for a reason in each round, by the way, between F and GH and between GH and F sub alpha, right? So we should be able to catch these things. Yeah, but we have a number of rounds, right? So intuitively, we have to at least pay for an error, which is going to be some union bound over a number of rounds, because the prover hasn't a chance to do this attack at every round, times the probability that each round's consistency check fails. Okay? So like intuitively, like we're gonna have to pay for some soundness error that grows like that. But for us, R is super constant. It's like logarithmic. Okay? Like we have a number of rounds. It's log D, right? So here we really have two options. We could say, all right, I'm just going to strengthen the consistency checks in each round and just make a bunch of them. In particular, make a super constant number of them per round, so that I'm going to catch, if you try to move more than a constant fraction, I will catch you with probability that is, say, 1 over log D. Okay? So I can sort of balance out this one here. Okay? That would have the effect that in the end, we're going to get more than a logarithmic number of queries, which is not necessarily bad, right? I mean, how many times you have to repeat this one? It's going to be roughly on the order of log D, right? To obtain a soundness error that catches with probability 1 over log D a drift of like constant fraction, okay? Yeah, but we want to get log D, okay? By the way, that direction you could go and analyze it, and you just basically strengthen a lot each round's consistency checks. But it turns out it's actually not needed, okay? You can actually change the protocol once more, and you get a protocol that will actually magically will only make a constant number of consistency checks per round and still somehow be fine, okay? Which is very, very surprising, okay? So, is it clear the intuition between folding, the fact that intuitively folding, prevents distance from decaying fast, and secondly, that we have consistency checks to make sure that you cannot drift by being inconsistent with prior functions closer to low degree. Does that make sense? So there's a question about whether folding solves both the problems of having a linear number of queries and of distance decay. Yes, it solves both. More questions?
Maybe to check the intuition. Now, once we start folding, sort of a stupid prover could accidentally have the function drift away from being low degree, right?
A prover can also stop talking and refuse
Okay.
So clearly it can send functions that are have nothing to do with the original one, among other things, right? Maybe they are low degree even, right? But they're low degree about some other execution for some other low degree F, right? By the way, this is going to significantly complicate the soundness analysis. Like the fact that the prover can try to do various things. It could sprinkle noise about F. Halfway through the protocol, it says, yeah, I got tired. Let me start like talking about a different F, some noisy execution for a different F, right? Or just send some total garbage altogether. It's like far from absolutely everything. And all of these cases are gonna really complicate a soundness analysis, okay? But yeah, all of those are options. But intuitively, if it sends, like the intuition is that if it sends something that is far from F, the consistency check should catch them. And if it sends something that is close from F, then it cannot, because of folding, become closer and closer to low degree too fast, okay? And therefore, like at the end, if you had started from far, you cannot just write down something that is low degree, okay? Yeah, but the attack surface is somewhat rich, but I think the intuition is there. All right, so let's talk about the protocol that we're actually going to study, the FRI protocol. So there are going to be two changes from the prior protocol. The first one is kind of a bit of a silly thing that actually we don't really need G and H to be sent, okay? As we'll explain in a moment, even for the prior protocol, as it was looking already, G and H was just, I don't know, for us to kind of build up the intuition, we don't need to send them, okay? You can basically imagine G and H on the fly by yourself as a verifier. So we don't need them. I'll explain that in a moment. Secondly, the main sort of secret sauce of the protocol is that in order, it's not going to do number of rounds independent consistency checks. It's going to do a single consistency check that is correlated across all rounds. And this single test will have constant soundness error. Okay? So it'll be a correlated test. This is not a protocol you can analyze, let's say, recursively. Like the prior protocol, you could have analyzed recursively. Like you kind of analyze this one round reduction, and then you kind of use induction. We will not be able to do that. We have to like analyze the entire protocol as one big thing because of this single multi-round consistency check. All right, let me first kind of clarify this part over here. So we're going to define this folding operation more formally. So you give me a function, not a polynomial, just a function, okay? And some kind of pivot here, alpha, right? And I can define fold of f alpha itself is a function defined over the square of the domain. And this function at a particular square will return the output, which is this contribution from f and this other contribution from f, linearly combined. Okay? Why this one? Because this is the evaluation of the polynomial that corresponds to the even and odd coefficients. Why? Well, for every square, if I look at this value of the even coefficients and the odd coefficients together, it's kind of easy to check and can explain it. Look, if you wanted to see the contribution of the even coefficients, right, you can just evaluate f at gamma and f at minus gamma. Because you put the minus there, all the odd things are going to just drop out. The even things are going to stick around. There are going to be two of them, so you divide by 2, right? And everything is going to be squared, right? So that's why we're talking about squared, because remember, this is a new polynomial where all the even coefficients have been they're not still about the original monomials, they're about the monomials of half the degree, right? So that's why there's a square here. And something similar happens for the odd ones, except that you have this kind of x that gets factored out, so you have to kind of pull it, you have to divide by it as well, right? So this expression and this expression agree on so many terms, so they must also be the same polynomial, okay? So kind of this folding operation is as if you had given me G and H already directly from F, right? I can create G on the fly and create H on the fly, okay? And then, then I fold. So these changes lead to the FRI protocol, which is described as follows. So here it is. So first, the verifier is going to sample interaction randomness for each round. I am sampling all at the beginning just because I wanted it to fit in half a slide. Otherwise, you would sample it as you go through each round. It sends the first pivot to the prover. The prover will fold the function around alpha 0. It will get this smaller function, it will send it all over, okay, half the size. The verifier is going to send the next pivot. Prover is going to fold, send it, and so on and so forth until the last folding, okay? And things get smaller and smaller and smaller. At some point, you get sort of a constant size domain. All right, so far nothing has happened. It is just an interaction, okay? So it's a public coin protocol. Now, a query phase starts after the interaction. The verifier is going to sample a single element of the original L that is going to define consistency checks between every round. So you run consistency checks between F0 and F1, F1 and F2, F3, F4, and so on and so forth. The first one is going to look like this. It's going to say, all right, if you really claim that this is the folding of F0, let me check it at the random point I sampled. I query F1 at mu squared, and I see whether the expression for folding really holds, right? Okay, but that's just between f1 and f0. You also claim as a prover that f2 is the folding of f1 around alpha 1. Let's check that as well. I already have mu. Let's check it at mu to the fourth, right? And I check the folding operation relative to that. Okay? And I do the same until the very end. Okay? And notice that it's the same mu, right? Because sort of mu squared is in L squared, mu to the fourth is in L to the fourth, and so on and so forth. This defines consistency checks between all rounds. All right? Now I'm not done. I also need to, at the very end, make sure that the last function you sent me really is a loaded degree, right? Because if I don't check that, you can just be consistent throughout. At the end, you have something that is not low degree, and you won, right? So you have to check something at the end as well, right? So kind of I'll come back to in a moment. The query pattern is kind of this kind of lopsided tree. You query the first function at the element and minus its element. That defines a square in the next domain. You query the next function, and this is like, this triangle is this consistency check. The next triangle queries sort of that square and minus, oopsie, that should be a square. Minus that square, right? That defines a fourth power over here, and so on and so forth, right? So that's a logarithmic number of queries. But they're all correlated, right? They're not just like random triangles in each round, they're all kind of aligned. Okay. Now, we will also see what happens with this parameter t. You can imagine running this query phase multiple times to boost your consistency test without rerunning the protocol. I mean, the protocol has been run, right? In the query phase, you're just asking, instead of log d queries, t log d queries. Okay. And this is the protocol that we want to analyze. Okay. Are there any syntactic questions about the protocol? Notice that we are still doing basically a consistency check between this one and the folding, except that you didn't have to send me G and H about F0 because here is G and here is H. Okay? So G and H were just some crutches for us to think about what to do, but they are anyways local maps that we can compute on the fly.
So essentially, because you're checking consistency of all the queries, you don't need to do a load degree tests for each like intermediate one as well.
Yeah, so let's go over the intuition. So I want to load degree test this one, right? And if this one is far, we think that with high probability, its folding, not we think, we know, or at least we will prove that with high probability, its folding will also be far from low degree, the same far, okay? But because, I need to continue, I need to materialize it in order to fold further. Otherwise, like my kind of, if I don't ask him to send the things in between, my query complexity is going to explode, right? Because querying the folding of the folding of the folding of the folding, that is going to depend on like 2 to the number of queries, right? So that's not good, right? So I ask the prover to materialize the folding for me so that later I may fold it again, but the prover may lie, right? So I have to check that it is really the folding. And to the extent that it is the folding, it must also be similarly far as F0, okay? And to the extent that this one is similarly far as F0, then its folding must be similarly far to the extent it is the folding, right? So at every round, the prover has the option of either kind of sending something that is very consistent with the previous one, in which case this folding property is determined that its distance cannot go down, or it can expose itself by sending something that's a little bit inconsistent, in which case it will expose itself to being caught by one of these, right? At some point, the problem becomes folded enough so that it is of constant size, and we just check it, okay? And because distance was preserved throughout, then so in the end, so that makes sense. More questions? Right, this is a really beautiful protocol. Now we'll see the analysis. And also it's incredibly fast. Like this folding operation is linear. Okay, this is like, some very simple logarithmic number of field operations. It's like, very stupid checks here. Yeah, this is like, it's really like not just like a nice protocol, it's also very practical.
You mentioned that this cannot be analyzed recursively, but we could like do these consistency checks every round. So, and then why can't we do a recursive analysis?
Because it's correlated. You cannot just have a recursive call on some independent randomness. Like the randomness sort of is shared across all rounds. So what you can do instead is like not do this protocol, but do a different protocol where you do independent checks at every round, but then you have to boost each round's independent checks to be like kind of super constant strong so that you can withstand a super constant number of rounds and pay the union bound there. Here, you will actually not pay a union bound. The consistency check, this consistency check has on its own a constant soundness error without any union bounds. Yeah, good question. Okay, so we're going to just build some intuition for the rest of the lecture. We won't actually get into the analysis, and then we'll spend all of the next lecture doing analyzing it. So the first thing, let's just kind of do all the relevant things, including completeness. So first, let's argue it has perfect completeness. Okay, this is just to build some intuition. Suppose that the original function that is written down over the domain L really does have degree strictly less than d. Now, fix any choice of interaction randomness. Remember, for perfect completeness, it means that we have to show that things accept regardless of randomness. So fix some choice, arbitrary. And for every round, we can define a polynomial, which is the even and odd folding around the correct randomness of the previous polynomials, right? Again, now I'm defining everything in terms of polynomials. Now, from these polynomials, because this original assumption holds, then we know that each of these polynomials has degree that is strictly less than d over 2 to the I. And therefore, if we evaluate them on the corresponding domain, they will be in the correct Ritz-Solomon code with the right power here and the right power there. And this function is precisely the folding function that is used by the honest prover, right? Because this is what the honest prover does. Okay? Why? Because we already checked this, right? So if you give me some function if you give me some element and I evaluate the next function at the square, well, by definition, by construction, this one was the valuation of this polynomial. So here it is. But the contributions on the odd and even are precisely given by these expressions, okay? But this is the value of fold, right? So it means that this correct, or this low degree function that is computed by the prover at each round really is the folding. So folding is the correct thing to do, okay? And therefore, for every mu, all of these checks will pass. And finally, as argued above, this final one will be in the correct Ritz-Solomon code. And so all the verifiers degree check pass. All the verifiers checks pass, whether consistency or degree. So, okay, so this was just kind of going over again sort of the syntactically how the protocol looks like and what is its intention. The prover time is linear. It's actually not even, it doesn't even need the polynomial representation of the original function. It just needs its table, which is there, and it just folds it. Those are local maps, linear time each time. So overall, you have a linear time prover. The verifier time is sort of a constant number of field operations per round, plus sort of doing some interpolation at the end over this final domain. The final domain has this size, and all of this is logarithmic in D when R is log D, and the degree is linear in the domain, which is the regime where we're working. And the query complexity is also clear. It's a similar computation because you make you're making a constant number of queries per round, and in the end you have to read all of this function that is L over 2 to the R. And actually, when R equals log D, this is actually going to be a constant, so you don't even need to, because it has constant degree at the end. Degree 0. So in the end, you don't even need to send me like a table, you just send me the constant that represents that table when R equals log D. Yeah, so kind of, I think all the syntactical things hopefully make sense, that we're all in the right regimes. Are there any questions about this slide? So before we move to soundness, it is helpful to think of just a simple attack. It's not really like an attack. It's just, every test has its limits, right? When you prove that a certain PCP or IOP or test or whatever has a soundness error at most, blah, blah, it also has a soundness error. There's at least something, right? Because the test is not perfect. So one way to gain intuition about what is the ballpark or what type of statements you would want to prove, you have to first at least understand, well, what can the prover do, right? So let's build intuition by proving that there is a prover strategy, in fact, an efficient prover strategy that makes the verifier accept some delta var f0 with probability that is at least 1 over f. This is going to tell us that dependence on field size is necessary, okay? And, is going to be a lower order term for larger fields, but for smaller fields, this is something that you have to account for. And also some other term that is should look familiar and nice, which is it basically views the probability that all t queries to f0 don't see any noise, right? So f0, if it is delta var, and you're going to be making t queries to it, like, look, those t queries could just all land where there is no noise. So you can't expect to do better than that, right? This is the probability that all of them fail to see the noise, okay? So you would expect there to be an attack that works at least this well, right? Because if those queries land to the non-noisy part of f0, technically there should be like an honest execution from there onward to make everything else check out, right? Does that make sense? So this should look like a natural sort of, let's say, type of attack. In particular, you cannot expect, I don't know, like some very small quantities. Like you're not asking do too many queries to f0. If you can't see the noise, then you can't catch anything, right, later on, right? So, all right, so let's talk about it. So here's the idea. So we're going to take the original L, and we're going to split it into two sets. Let's call them L0 and L1. L0 is going to be sort of the large non-noisy set, and L1 is going to be the smaller noisy set, okay? But also I want to split them not arbitrarily. I also want to keep elements that square to the same the square to the same element in the same set, okay? So if for whatever reason I put a particular mu into L0, then minus mu I also want it to be in L0, and ditto for L1, okay? So I just split them up by keeping pairs together. That I can do, okay? So now we have to exhibit some f0 and a strategy for that makes the verifier accept at least with this much, right? Crucially, this f0 has to be delta var, otherwise there's nothing to do. Otherwise I give you like a f0 that is low degree and I can make the verifier accept with probability 1, right? So the challenge here is that I need to write an f0 that has noise and argue that the verifier will accept with this probability, right? So here's the f0 we're going to write down. We're going to put zeros everywhere on L0, okay? So it's mostly zeros. And then there is this delta fraction where we put something non-zero. And what do we put there? We're going to put a line, okay? We're going to put the evaluation of a line. So we take a degree 1 polynomial. And any polynomial that has degree 1 that just doesn't vanish in L1. So I want this to be like a line that has no zeros over L1. So it's all non-zeros, okay? Now, notice that f0 is delta var from low degree because the closest code word is 0. There are no other closest code words. And this differs from 0. Okay? And so that's all noise. Okay, so it's delta var. Okay, making some minor assumptions that the degree is, I don't know, like a tenth of the size of L, and then D is like 1 minus D is much larger than that, okay? 1 minus delta times L is much larger than that, okay? Okay, so all of this is actual noise. So now let's see what happens when we start running the protocol. Well, first, the prover is gonna always, from now onwards, just kind of do this honest execution, right? Because if you had really started with the all zero function, what you should have done is to send 0 every time, the 0 function every time. So it's gonna continue honestly as if he had been thinking about the all zero function. But f0 is not the L0 function. It is primarily 0 except for some delta noise. Now let's see that first and foremost, kind of no matter what alpha zeros are being sent, alphas are being sent during interaction, if the consistency checks never see the noise, then we accept, right? Because if if here you get outside L1, outside L1, outside L1, outside L1, you can get 0 plus 0 divided by 2, plus alpha 0, 0 minus 0 divided by 2 mu. What do you get? 0, right? Why? Because that's what you should have gotten anyways, right? That was the honest execution. So if all the consistency checks land in this location, it's as if the function we started with really was the 0, 1, and answering 0 every time is the honest execution, right? So the probability that all of the tests fail to see the noise is this one over here, okay? At the same time, no matter what is the consistency check, and no matter what randomness we have later on, in the first round, it could be that alpha 0 is a root of the line. And so that we get a function, basically this will evaluate to 0 even though we started from a function that was non-zero, right? Because it was a line. All lines have zeros, right? Somewhere in the field, okay? That 0 is not over L1, but it was going to be somewhere, okay? And it could be that alpha 0 is that 0, okay? And so we may still accept in that case because, f1 is consistent with it, with this local map, okay? And that's what it is. It doesn't matter what mu is, just alpha 0 is a sort of a 0 of that line, okay? Now, 0 is just representative. Everything is linear. We could have shifted up to start from any low degree polynomial that we are adding noise to. Just 0 is the easiest one to think about. It is the easiest low degree polynomial to think about to start with. But you can start from any low degree polynomial and sort of sprinkle up noise like that, okay? But this is telling us that, okay, well, there is this fairly silly strategy that tells us, whatever we're going to prove about soundness, it can't be better than this. There's going to have to be some dependence on f, and there's going to be some term that, cannot be smaller than 1 minus delta to the t, okay? Because again, 1 minus delta to the t is sort of the probability that we don't see any noise at the beginning. And 1 over f is the probability that somehow we start with the noise and there's a chance that the noise kind of becomes consistent, okay? All right, are there any questions about this attack? It can be improved, by the way. You can try to play these games, across multiple rounds and you're gonna get some bigger term here. All right, so I highly encourage you before next time to think of this attack and think of other attacks as well, to just think as a prover, what could you do and why can you or why can't you, okay? It's gonna be very important for the intuition, to have that intuition when we go over the analysis next time, okay? Now, in terms of what can be proved, so I'm just repeating the soundness error. The upper bound is to a first order, like pretty close to it, okay, what we can prove. Here's the proof, and here's the theorem statement. Give me f0 that is delta far, okay, and give me whatever malicious prover strategy. So he gets to, obviously, to choose to send whatever oracles it wants through the interaction. So this is written basically let me first maybe write the corollary first. The soundness error is at most, let's first focus here, maybe I'll switch it later in the slides. The soundness error is this one, okay? Notice that kind of this term over here kind of reflects this one over here, something over f. Now, the numerator is a bit larger, is L over f rather than 1 over f, okay? But, still something over f, and for over large fields, it's usually something that you're not gonna really worry about, okay? In the second term, let's color it this one, it's kind of analogous to this one over here. It is basically like 1 minus delta to the t, except that it bottoms out at some point, right? If delta is too large, if you're too far, then we can't really say that you're really going to reject with that much probability. This should not look alien when we discussed linearity testing, when we discussed low degree testing. In both cases, we had this bottom-up, the saturation behavior, that if the distance was too far, all we could say was the rejection probability was above something, okay? Or similarly, that the acceptance probability is at most something, but not something too small, okay? And here we have some constant here, okay? C is a universal constant that depends on the ratio between the degree and the domain. The ratio of the degree of the domain is called the rate of the code. There is some universal constant that depends on the rate. And if you're too far, you don't pay for the distance of how far you are, you pay for some constant that depends on the rate, okay? But qualitatively, the upper bound is really very close to the lower bound, okay? Now, what the formula will actually prove it is a slightly stronger statement that says with high probability over the interaction, the probability that a consistency check fails, or at least accepts, is at most something that decays like that, okay? That as the distance increases, it goes down up to a certain level, okay? And of course, you're welcome to do more and more consistency checks to drive this down without repeating the interaction, right? This constant right now doesn't matter. All that it matters is that it's a constant for now, okay? And we'll prove the theorem in the next lecture. The proof relies on fundamental statements about worst case to average case distances to subspaces. This precisely kind of how does distance behave under folding. We'll see it in specific settings, but those are phenomena that actually hold for every vector space, every linear code. And actually, this is not the best form of the upper bound. Like the gap between lower bound and upper bound is a sort of very active research frontier, and tighter upper bounds have been established using rather non-trivial tools, using algebraic geometry and algebraic function fields, and somehow sort of understanding how precisely the soundness of this protocol works is something that takes you very far afield into, I guess, more mathematics than even protocol design. And these improvements, the fact that you can somehow squeeze more out of these expressions, have like a pleasantly sort of noticeable effect on practical efficiency of this protocol, because of course, as the soundness error gets better and better, you're going to do fewer repetitions. Maybe you can set the fields to be smaller and things like that, right? And so kind of the study of protocols in this regime, in particular this protocol here, and understanding the exact tight soundness analysis, it remains an exciting sort of open problem. So I'm going to stop the recording now.